Okay, guys, welcome to Physics 390 Class 12. In this class, we'll be talking about the hydrogen atom part 2. And whereas in the first class, we looked at the central potential and the solutions to the angular part, which were the spherical harmonics, concentrated on that. In this part, we will be concentrating mostly on the radial part of the radial equation, which comes out of the separation of variables of the TISE in 3 dimensions. we'll be looking at the solutions, the full solutions, the combined radial solutions and the angular solutions together. And we'll also look at some visualizations of the hydrogen atom solutions or stationary states. And this comes from chapter 4.2 of our textbook. Okay, so the TISE, the time-independent Schrödinger equation for the hydrogen atom, we'll look at, and we'll do some rearrangement of it and start to look at the asymptotic behavior of that for large r, at large r and small r, to start trying to solve it. So recall that the TISE in 3 dimensions is this, which looks like the TISE in 1 dimension, except that we have del squared instead of d dx squared. So that's the Laplacian there. For the hydrogen atom, which is sort of a little cartoon is pictured up here, we have the proton in the center with charge plus E, and the electron out here with charge minus E, separated by a distance r. Of course, this is in the plane. It would be a sphere, a 3-dimensional model. So using spherical coordinates for the central potential, the potential is V of r is minus E squared over 4 pi epsilon naught 1 over r. So it'd be plus E times minus E, which is minus E squared. 1 over 4 pi epsilon naught is the same as the Coulomb constant, and it's 1 over r because it's the potential energy. 1 over r squared gives the electric force. So that's our potential. So as we saw previously, we can separate this TISE into an angular part using separation of variables, which are solved by the spherical harmonics y, l, m, theta, and phi. And then a radial part, which is written as minus h bar squared over 2m, m being the mass of the electron, second derivative of u with respect to r squared, plus this business here, which is the Coulomb potential, plus this extra term, which is often called the centrifugal term, which keeps the electron from getting, it tends to fling the electron away from the nucleus, has to do with angular momentum. So times u is equal to EU. Now recall when we separated the variables, it was YLM and capital R. But to make a little bit simpler equation and to make progress towards solving, we introduced another function, u of r is equal to little r times the big R function. So our function is written in terms of u instead of big R. But if we solve for u, we could immediately get big R as just u of r, u divided by r. So it's, if we solve this equation, we've solved for capital R as well. So, oh, and this is a graph of the term in brackets here. You can see the first term goes as minus 1 over r, so that would decrease, and that would keep decreasing down here. But the second term goes as plus 1 over r squared. And as r gets small, r squared, 1 over r squared dominates over 1 over r. And so we get it shoots up and goes to plus infinity as r goes to 0. So we actually have a minimum in this potential here. And this is called the effective potential, V effective. That's this term in brackets here. So that's the potential we're dealing with and trying to solve here. So we're aiming to solve for the eigenfunctions u of r and the eigenvalues e. that is the allowed energies for the hydrogen atom. So we first write, kind of clean up this equation even a little bit more than we have already. We express the energy as, now remember the energies are negative because these are bound states. The electron is bound to the proton. So the overall energy is going to be negative. So when we take minus 2m electron e, that's a positive number. So when we take the square root, this is a real number. And we call that over h bar kappa, okay, just to kind of clean up notation. And then we express a scaled radial variable. Rho is equal to, or defined equal to, kappa times r. And then a specific constant comes up when we substitute this in for r and kappa in for e and try to clean up the equation. And that is rho naught, which is this combination of constants. Notice it's related to kappa, and kappa is related to e. So rho naught depends on e. So if we get a specific value of rho naught, we can solve for, since these are all constants, which we know, we could solve for kappa, and then with kappa, we could solve for e. So solving for allowed values, eigenvalues, or allowed values of rho naught would be the same as we could, from that, we could deduce the allowed values of the energy E. Okay, so there's some steps here between this equation with the U of R and this is equation of U of rho, the scaled radius. But you can look at the textbook for those steps, but it looks like this. It does clean up some constants a little bit and make it look a little bit more manageable. So we have the second derivative of U with respect to rho is 1 minus rho naught over rho plus L plus 1 over rho squared U. Okay, so that's what we're trying to solve. And if we solve for U, we get capital R, the eigenfunctions. If we solve for rho naught, we get the kappa and we get the E, we get the eigenvalues. So that's how this would work, would translate back to our original radial equation. Okay, so I said we were going to look at asymptotic behavior. That's one of the advantages of putting the equation in this form. So if we look at large rho, which would be large R, as rho goes to infinity, this equation, since rho is in the denominator here, rho and rho squared, these terms would get very small. So we just have the second derivative is equal to 1 times the function. D squared, the second derivative of u is equal to u. And that's solved by an exponential. It has to be a negative exponential so that it drops off to 0 at infinity. So it's has a chance of being normalizable. So as rho goes to infinity, this would be solved by u of rho is approximately a e to the minus rho. Okay, so just a decreasing exponential. The other limit we can look at is not big rho or big R, but little r, so getting close to the origin. So as rho goes to 0, since rho is in the denominator here, this term would get pretty big because rho is getting small, but this term would even get bigger because it has rho squared, and rho is, as rho goes to 0, 1 over rho squared dominates 1 over rho. So we just get this term L times L plus 1 over rho squared. So our equation becomes, the second derivative is L times L plus 1 over rho squared u at rho goes to 0. So that's solved by u is some constant times rho to the L plus 1 power. And if you want, you can verify that. If you just take the second derivative of this and compare it to what you get on the right side, you find that they are equal. Okay, so those are the asymptotic behaviors: negative exponential behavior at large rho, and this power law behavior, rho to the L plus 1, where L is the index of the in the angular part one of the indices in the angular part, +1. Okay, so how does that help us? Well, we're going to use the asymptotic behavior. We're going to see that it's going to lead to another power series solution. Remember, we did a power series solution for the harmonic oscillator. That was one of the ways we solved the harmonic oscillator. And we'll see that there are a lot of similar features and a similar way that we restrict the values of energy by terminating the power series. Anyway, using the asymptotic behavior, we introduce another function, v of rho, by incorporating the asymptotic behavior. So we write u of rho, which is what we're trying to solve for, as the rho L to the L plus 1, which is the small rho behavior, times e to the minus rho, which is the large rho behavior, times v of rho. So hopefully by building in the small rho behavior and building in the large rho behavior, we're going to get, and looking at the rest of the behavior as v of rho, we can solve for what the main behavior is between the low rho and small rho and large rho behavior. So after plugging this in and rearranging terms, and again, I refer you to the textbook for this, there are several steps here, we get this new radial equation. Rho, second derivative of v with respect to rho, plus 2 times this constant, first derivative plus another constant involving rho naught, which involves the energy, times v. Okay, so this one looks pretty, once we've peeled off this asymptotic behavior, it hasn't gotten, it's arguably less simple or a little more complex. So it's a tricky one, just like the harmonic oscillator differential equation was. So we're going to use a power series solution, which is one of our most powerful techniques for getting the giving the difficult differential equations. So as for the 1D harmonic oscillator, let's try a power series solution. We let v of rho be equal to the sum from j equals 0 to infinity of coefficient cj times rho of j. So it's a power series in the variable, our independent variable rho, with all powers of rho, each with a separate coefficient. Then we're going to need the derivative of this function, dv d rho. So we take the derivative of it. The first derivative, it pulls down a j, and a rho becomes j minus 1. We still have the cj. And then notice the first term here is j. When we plug in j equals 0, this j is 0. So the first term is 0. So this sum really starts with significant terms from j equal 1. And at j equal 1, it would be 1 times c1 times rho to the 1 minus 1, or 1. So it would just be c1. So we can sort of re-index this starting from j equals 0, so that we can compare it easily to the to v, the power series for v, as j plus 1, cj plus 1 rho j. So just added 1 to each of these indices and started it from j equals 0. So just to check that, again, the j equal 1 term here was c1. The j equals 0 term here would be 0 plus 1 times c0 plus 1, or c1, times rho 0 or 0 or 1. So it'd be c1 again. And we can check the second term. Here j equal 1 would be j equal 2 here would be 2 c2 times rho. Over here j equal 1 would be 2 c2 times rho. So they're the same. That this series is just so we can compare it. Actually the first term is significant. It actually gives a non-zero answer, j equals 0 here. And then we take the second derivative of that. We pull down a j, and rho goes to j minus 1. So we get this. Then what do we do with power series solutions? Well, we insert these into the appropriate places. So this would go here, this would go here, v would go here, And using the fact that each, if the left side here is 0, if we express the left side as a sum over some coefficients times the powers of rho, it can only be, that sum can only be 0 if each power of the coefficient of each power of rho, so coefficient of each rho j must be 0. Okay, and when we do that and set all those equal to 0, we get a recursion relation, which relates the coefficient Cj to the coefficient Cj plus 1. Okay, so when we set, you can see that Cj and Cj plus 1 are all involved, are the C's that are involved in the a given j, and so that we get the same recursion relation for all j. So this would tell us, given if we started out with a given C0, just a first coefficient, which would be a constant coefficient since rho 0 is 1, so it'd just be a constant. Then we could, and we know the value of L and rho naught, we could get j plus 1, Cj plus 1, just by plugging in this equation. And then once we know C1, we plug it in here, plug in the appropriate values here, and we get C2. So this determines all the coefficients Cj given C0. Okay, so that's the recursion relation that comes out of the power series solution. And we had something similar for the harmonic oscillator, although it was a different recursion relation, since that's a different system with a different potential. Okay, so again, the theme is that the power series must terminate. That's what we saw in the harmonic oscillator. And that's what gives rise to the allowed energies, what we call quantized allowed energies for the hydrogen atom. So how does that work? Well, here's the recursion relation again. And for large J, so we look at large J. So we assume the series doesn't terminate. So at large J, this power series will be, or sorry, this recursion relation will become C to the J plus 1 is approximately, so this, as J gets very large, L can be neglected and 1 can be neglected here. So we just get 2J, and rho naught can be neglected. So we just get 2J in the numerator. In the denominator, we have J plus a J here and a J plus 1 here. So we get 2J over J plus 1, or 2 over J plus 1 Cj. So this would be for large J, this simplifies here because a lot of these variables are very small compared to J. So we get 2 over J plus 1 Cj. So every time we increase J to J plus 1, we're multiplying by 2 over J plus 1. So this recursion relation at large J is approximately solved by saying Cj would be basically 2 over J multiplying by 2 over J each time we go from C0 to C1, C1 to C2, C2 to C3, etc. So we'd get J factors of 2, and then in the denominator, we would get J factorial, because first J would be 1, then it would be 2, then 3, then 4, then 5, then 6, which becomes J factorial. So we get our approximate solution then is Cj is 2 to the J over J factorial C0. So inserting that approximate solution into our power series for our desired function V, so inserting that Cj here, gives V equals C naught. So we can pull out the C naught since it's a constant, doesn't depend on J. 2 to the J over J factorial rho J. Now, we can put this 2 rho together, 2 and rho together, 2 rho to the J over J factorial sum from 0 to infinity. And that's the expansion of e to the exponential. E to the x is the x to the J over J factorial sum from J equals 0 to infinity. So here playing the role of x is 2 rho. So this would become C0 times e to the 2 rho, since it's 2 rho that's being raised to the jth power here. Okay, all right, so big deal. So now we've got the v of rho. It would be, assuming the series gets very large, there's a lot of terms in it, would go as e to the 2 rho. So what does that tell us? Well, we go back to the definition of u of rho, which is what the first function we were looking for. U of rho was, after we put in the exponent, the asymptotic behavior, rho L plus 1 e to the minus rho times v of rho, but v of rho is C0 e to the 2 rho. So if we put in that C0 e to the 2 rho, the e to the minus rho, which was the previous asymptotic behavior, times the e to the 2 rho becomes e to the rho. And we have C0 rho to the L plus 1 e to the rho. So our u, which was the radial equation we started this with, it's of course the one in R is the very, very original one, but u is very closely related to the R function. So anyway, the u would diverge at large rho, that is at large radii. And that would, because e to the rho will blow up as rho gets large. So that leads to a wave function that is not normalizable. So the only conclusion is, what we assumed was that we get to large J. So we must not get to large J. That means the power series must terminate. So if the power series must terminate, that means at some point the numerator of this recursion relation must be 0, because we must have a finite value at, say, Cj, and Cj plus 1 must be 0 for some j for it to terminate. So that can only happen if the top is 0. So, so the numerator must be 0 for some j. Letting n equal to j plus L plus 1, just to kind of tidy things up a little bit, the condition would become, the numerator going 0 would be 2 times this, which is n, minus rho naught equals 0, or rho naught equal to n. Okay. But rho naught involves e. Remember, we emphasized that on a previous slide, because rho naught is related to kappa, and kappa is directly related to e. So according to this equation here, e is related to kappa, and kappa is directly related. Rho naught was defined in terms of kappa. So we can, if we know rho naught, we immediately, because these are all constants, we immediately get e. So this condition means that rho naught, the condition for the numerator to be 0 is that rho naught be equal to 2n, where n is an integer, which can be 1. It can be 1, 2, 3, 4, 5, 6, any integer, because L starts at 0 and J starts at 0. So the lowest n can be a 0 plus 0 plus 1, and these grow from there. So n can be, starts at 1 and can grow as an integers from there. So plugging in 2n for rho naught here, where n is an integer, and then simplifying some, or rearranging some terms here, we get the following equation for e, e subscripted by n, because n equal 1, 2, 3. So this is the same equation as we have here, just with 2n put in for rho naught, which is again the condition that the power series terminate. So it's and so that becomes minus this constant times 1 over n squared. So it's minus, and we call this, since when n equal 1, e1 would be minus this constant. We call minus this big constant here e1. Okay, and we'll give the value of that in a second. So So the fact that the power series must terminate gives a condition on rho naught, but since rho naught involves E, that means it gives a condition on E. So it's the fact that the power series must terminate that gives us only certain allowed values of E indexed by the integers n equal 1, 2, 3, etc. Okay, so, and that's similar to the harmonic oscillator, where we found only certain allowed energies for the harmonic oscillator. In that case, they were equally spaced because the power series for that one must terminate as well. All right, so let's see what we get from this, the hydrogen stationary state. So we're kind of ready to look. So the energies we see depend on n as En equal this E1, which was this big combination of constants on the last slide, over n squared. And it turns out to be, if you calculate it, minus 13.6 electron volts. And electron volts are a pretty small amount of energy, as you might expect. 1 electron volt is 1.6 times 10 to the minus 19 joules. But that's appropriate because the atom has pretty small energies. So 13.6 electron volts would be something like, 10 to the minus, roughly 10 to the minus 18 joules. So we're dealing with small energies because the atoms are quite small. So the energies only depend on n. They don't depend on L or M for this basic model of the hydrogen atom we're looking at. The stationary states, on the other hand, the eigenfunctions depend on n, L, and M. So psi n, L, M as a function of r, theta, and phi. Remember, we divided it into r and y, where y, L, M are the spherical harmonics, and r was the radial function. And it depends on n and L, as we'll see in a second. So we can find r and L as, remember, r is equal to u over little r, because u was defined as little r times the big R function. So big R is u over little r, but then we wrote u as rho L to the L plus 1 e to the minus rho v of rho. Okay, so v of rho, and rho, of course, rho is just a scaled version of r. So that's why it makes sense for us to say big R of r is something involving rho, because rho it turns out to be kappa, this r constant times r. So it's this rho is linearly related to r, so it's still a function of r. Where v of rho we saw is a polynomial of degree, a polynomial which is related to some class of polynomials called the Laguerre polynomials. Okay, so you can look at your textbook for there's associated Laguerre polynomials and Laguerre polynomials, and you can look at your textbook for examples of those and formulas related to those. I just want you to be aware that the radial functions of the hydrogen atom are associated with the Laguerre polynomials, after a French mathematician named Laguerre. And remember, we had n was equal to j plus L plus 1. That's what we defined n as. So the polynomial is degree j, because that's the index of the series. And j is equal to, if we solve this for j, it's n minus L minus 1. So the polynomial has degree n minus L minus 1, the polynomial v. So that means that the r, the v function, and therefore the r function, depends on L as well as on n, because the polynomial its degree depends on both of those. So that's why we index the r by n and L. All right. Okay. And that polynomial, I should say, is the power series which terminates. A polynomial is a infinite power series which stops because it's 0 after a certain entry. Okay. So this, the fact that the polynomial is degree n minus L minus 1 leads to a restriction on L. It has to be 0 up to n minus 1. Okay, so for n equal, if L was bigger than, this can be written as n minus 1 minus L. If L was bigger than n minus 1, this would be a negative number. And we can't have a negative number for the degree of a polynomial. So the biggest L can get is n minus 1. So in this n minus L minus 1 would then be 0. So L is restricted. According to the angular equation, it can be any integer, 0 up to infinity. But here, it can only go up to n minus 1 to keep this polynomial with degree 0 or higher. Okay, so for n equal 1, then, which is the ground state, the first state with the lowest energy, E1, this says that L would have to be 0 because n minus 1 is 0. So L would be equal to 0. And then the rules for the angular, so the spherical harmonics say that M runs from minus L to L. But if L equals 0, minus L to L is just 0. So that forces M to be 0. So that tells us that the ground state, or the first stationary state, has n equal 1, L equals 0, M equals 0. Okay, and it looks like this. Psi 1, 0, 0, n equal 1, L equals 0, M equals 0 of R, theta, and phi is R1, 0, since n is 1, L is 0, of R, Y 0, 0, L equals 0, M equals 0 of theta and phi. Okay? Now, we can show that with a little effort, we can show that kappa is equal to 1 over an, okay? Because kappa is related to rho naught, and rho naught was related to n. Rho naught was 2 times n. So where a is this combination of constants here, okay, so kappa is 1 over an, because again, n can be written in terms of rho naught, and rho naught was defined in terms of kappa. So anyway, for the details of that, you can see the text, but kappa can be written as 1 over an, where a is this combination of constants, which turns out to have a big physical significance, this a. It's called the Bohr radius, and it's really sort of the average size of the hydrogen atom. Now that varies with the state the hydrogen atom is in, but it's thought of as the characteristic size of the hydrogen atom, about 5 angstroms, or sorry, 0.5 times 10 to the minus 10, so 0.5 angstroms. Okay, so then we can write rho was kappa times R. That's how it was defined. But if kappa is 1 over an, rho will be R over an. So now we can put in for v of rho, we can put in R over an and get things in terms of R. So that means R10 would be, using this equation here, 1 over R times R rho to the L plus 1. But here R is, N is 1. So this is A times 1. And L is 0. So L plus 1 is 1. So we have R over A times 1 to the 1 power, e to the minus that rho, which is R over A times 1, times the V0, which is a polynomial of degree 1 minus 0 minus 1, or 0. So it's just a constant, which we call C0. So simplifying this, the R's cancel. We have 1 over A times C naught, so C naught over A times e to the R over A, okay? And then normalizing that, so it just turns out that C naught is 2 over the square root of A, So multiplying that by 1 over a, we get 2 over a to the 3/2. So that's normalized, the normalized radial function here. Okay, so that was going from using this expression here to go from our equation here for r, big R, in terms of v of rho, substituting for the relationship for rho in terms of r, and translating everything back to r, as we said we could in the beginning. Okay, then since y00, as we saw last time, is square root of 1 over 4 pi, it's just a constant, a normalized constant that's normalized over the angular integrals. We get psi 100 is the product of the normalized radial function, which is 2 over a to the 3/2 e to the minus r over a, times the square root of 1 over 4 pi, which if you combine these things, so 2 cancels with the square root of 4, pi comes in here, and we get square root of pi a cubed e to the minus r over a. And that's normalized. And there you have it. That's the ground state wave function or stationary state of hydrogen, which has an energy of E1 equal minus 13.6 volts over 1, or just minus 13.6, sorry, electron volts, not volts. Okay, so great. So what about other stationary states? What do they look like? And visualizations of them. Because visualization is very helpful to give us intuition for what the electron is doing in the hydrogen atom. Okay, well, first let's state that the stationary states psi and Lm of the hydrogen atom are orthonormal. So only if n, L, and m are the same for two states will their overlap integral be 1. If any of n, L, and m are different, their overlap integral will be 0. So that means they're orthonormal. They're also complete, meaning that we can express any function of r, theta, and phi as a weighted sum over all allowed values of n, L, and m. That is n integer 1 to infinity, L from 0 to n minus 1, and m from minus L to plus L. So summing up all that weighted by coefficients, we can form any arbitrary function well-behaved function in 3 dimensions. And then a second note before we look at the other states, the number of states with a quantum number n would be, so for n, L can be 0 up to n minus 1. So we'd have to sum up all those possibilities for L. And for each of those possibilities for L, we have m can be run from minus L to plus L, which is 2L plus 1 states. So we have the sum from L equals 0 to n minus 1 of 2L plus 1. So that's all the possible L states and all the possible M states associated with a given quantum number n, according to the rules that we've laid out before. And this sum, it turns out, is equal to n squared. Okay, so if you make this sum, which you can prove by, it turns out by induction. These sums are usually proved by induction. So for n equal 1, we get d, which stands for degeneracy, meaning multiple states with the same energy, because the energy depends on n. D would be equal to 1. For n equal 2, we'd get d is equal to 4. And those 4 states would be 2, 0, 0, 1, 0, sorry, 2, 0, 0, 2, 1, 0, 2, 1, negative 1, and 2, 1 plus 1. So there'd be four degenerate states with n equal 2, and 9 with n equal 3, and so forth. Okay, so just be aware of this degeneracy in the hydrogen atom. It's an important feature of it. Okay, so this is a table of some of the R, L, N, R, so some of the other states. This is the ground state here, which we looked at, 2 over well, the r part was 2 over a to the 3 halves e to the minus r over a. If we look at the n equal 2, we see that instead of e to the minus r over a, we get e to the minus r over 2a. And we get that for each one with n equal 2. We also get a polynomial here. Since n is equal to 2, the polynomial is of higher degree. Here the polynomial was of degree 0, so it was a constant. Here the polynomial is of degree 1. It has a single power of r in it. Of course, it's different, different polynomial for different values of L. Once we move up to r equal 3, we get e to the minus r over 3a. So you can see the pattern here. We have a, 2a, 3a, and then 4a for n equal 4, etc. And then the polynomials get of higher degree. So we have, here we have degree 2. That is, r squared is our highest, r squared is our highest power of r. Okay, so that's kind of the pattern. And the normalization constants are different because the polynomials are different, and so they require different normalization constants. Okay, so that's kind of the pattern. And then we could combine those with the appropriate spherical harmonic. So R10 would combine with Y00. R20, since L equals 0, would combine with Y00. R21 could combine with Y, so Y equal L equal 1. So that could be Y1 minus 1, Y10, or Y plus 1. So there could be 3 different spherical harmonics which combine with R21. And we get even more and more as we get L equal 2. There would be 5 different spherical harmonics which could combine with this one. All right, so that's kind of the flavor of what these functions look like. Let's look at some visualizations. So one way to do it is to do density slice plots. So this is a 3-dimensional function, so it's really hard to plot it, or you have to do something kind of special to plot it. So one thing you can do is just take a slice, and this is a slice sort of in the I guess the XY plane of the 3-dimensional space. So for 200, we see it's spherically symmetric because it would be paired with Y00, which is just a constant. So it only depends on R. So there's no angular dependence here for 200. Notice that there is one place where the wave function goes to 0, and that would be where this polynomial here in R20 would be 0, which solving that would be R equal to, let's see, R equal to 2a, where a is the Bohr radius. So where R is equal to 2a, this would be 0. So there'd be no chance of finding the electron at that radius, which is interesting when you think about it. Here's some other ones. I won't go into detail, but when L is 1, you get an angular dependence. So as you rotate around, you get different profiles. So there's an angular dependence. For 400, it's spherically symmetric because L equals 0. But there's 1, 2, 3 places where the wave function goes to 0. That's because there's a 3rd-degree polynomial in R40. Here's R410, 420, 430. So you get some really wild patterns, okay, as n starts to get bigger and L starts to get bigger. So the electron does some really cool stuff. Orbitals, these are, well, the stationary states, which in chemistry are called orbitals, are just quite stunning and quite beautiful coming out of this theory. Okay, and the second way you can represent these as sort of cutaway 3D plots, where you plot the where the wave function squared is bigger than a certain cutoff value. So this would be 200 with this again spherically symmetric. This would be 300 with two sort of 3 concentric spheres. This would be so various angular patterns as L is not equal to 1. Okay, so these are also a very nice way to visualize it. Okay, so just to summarize as briefly as I can, because we've gone through a lot, we looked at we're looking for the energies, allowed energies, and the stationary states of the hydrogen atom. We know the angular part is the spherical harmonics. The radial equation needs to be solved, and we can sort of recast it in terms of convenient variables, which become R and then U and then V for the functions, and the variables change from R to rho. And then once we get it in a nice form, we can solve that differential equation, the radial equation, as a power series. We find the power series must terminate. And the key idea is that because the power series terminates, we get a relationship between an integer, which we defined as n, which can be 1, 2, 3, or 4, and a quantity, which was rho naught, which is related to the energy. And so the energy can only take on certain integer values associated with integers. And that's that formula En equal minus E1 over n squared. And then we can roll backwards from our solution of the later differential equation, the later radial equation, to the original one, and get these functions of big R in terms of R, which we can combine with the spherical harmonics to get the full stationary states. And then we can visualize them really nicely. Okay, so hopefully that gives you a good idea of what the solution to the TISE for the Schrodinger equation for the hydrogen atom is. Thanks for your attention, and I'll see you all in class.